Thank you, Mark. It's a great pleasure to be here. And it's even a greater pleasure to spend a few months here. So I'm actually here until May. So I hope that maybe after this seminar people will actually find me. So I'm going to speak about, I assume that this is a wide audience and not everyone is expert on machine learning. Or how many of you know what deep learning is? Well, not all of you. How many of you know what mutual information is, just to make sure? Again, not all of you. It's a bit. All right. So I'm going to stay basic, although there are many advanced things that I would like to say, but stop me if you don't understand anything. So this is an ongoing work which I've been working on some aspects of it for many, many years. I mean, maybe 30 years. Before when neural networks just emerged in the 80s, many of the ideas that I'm going to talk about already conceptualized earlier then, and luckily the emergence of deep neural networks really made them very relevant again. So as I'm sure most of you know, when we talk about AI, you can easily divide the period since the early 50s, since Turing, into three very distinct phases. The first one is essentially what we call the logic phase, which is based on the very naive idea that you can program by asking an expert how you do things. I mean, for example, I ask you how you see, and you'll tell me, and I program it, and we'll have a machine that can see, or how you understand language, or whatever. As funny and ridiculous as it sounds today, this was the state of AI for essentially between the 50s and mid-80s, more or less. Although there were other ideas around, and there was statistics and other things that people used to do, but actually statistics met computer science more or less in the mid-80s, surprisingly. And with it actually changed the approach to AI by moving from rule-based expert systems to what we now call statistical learning or machine learning, which is essentially, instead of programming the rules, let's program the learning rules, which are some sort of a meta-algorithm which is supposed to fit data in some sense in a high-dimensional space. And this is what we now call machine learning, and that's more or less when I started to get interested in these problems in the mid-80s. I actually come from statistical physics and had no background in this directly, but indirectly, outside of my academic studies, I really did a lot of what we now call AI, even then, even earlier in the 70s and 80s. But as I said, so machine learning moved from AI moved from logic to statistics, and essentially most of what we call machine learning is essentially not much more than what Gauss suggested already 200 years ago, which is fitting high-dimensional functions to data. So essentially, this what we call a regression. You have data, which are those points here, and I'm trying to find a function which captures the essence of the behavior of this data. And of course, as anyone who actually deals with real data knows, there's always noise, there's always some uncertainty, and the problem is that we don't really want to fit the noise, we want to capture the rule underneath. And this is essentially the heart of curve fitting or approximation theory for many, many years. The issue is, of course, that we don't want to fit the training data, the sample that we get, but actually we want to predict the labels of functions outside of the sample, which means what we call generalization, or the ability to generalize beyond the sample. That's really the key fundamental question of machine learning or learning theory. I mean, how do we guarantee, or can we guarantee under some circumstances, that the prediction of new points here, which I haven't seen before, is not going to be too bad? And this is what we call generalization. I think I'm not going to offend anyone by saying that essentially all of the theoretical machine learning is some sort of fancy bounds on what we call the generalization gap, or how bad are we going to be on the unseen data, on what we call the test data, or in expectation of some other measure of performance, given the sample size And of course, we can't do it without assuming something about the function class. I mean, what type of function are we actually trying to fit? Because if I can fit anything, I can always get a perfect fit to the data, which is zero training error. But the function is going to oscillate like crazy otherwise. I think about polynomial of very high degree, or I don't know, very high frequency sinusoid or something like this. So the issue is actually how to guarantee out of training error, or what we call generalization error, under some assumptions on the class of function I'm trying to use. And this gives us to the iron basic rules of statistics. I mean, you want to, the number of data points should be of the same order, or actually better, larger, than the number of parameters you're trying to fit. Otherwise, you're going to overfit. I mean, this is something which anybody who did a lab in first year physics or something knows. I mean, you're not supposed to fit, if you have 2 points, don't try to go to very complicated functions, or if you have, and so on. Now, so this is the basic rule. I mean, and this is, and machine learning is all about refining and making it slightly more powerful, or more general, more robust. But essentially, that's it. How to fit simple functions through complex data in a way which will generalize well. This is at least what we call the information complexity, or the sample complexity problem. There's an additional issue which I must mention here, because which is the computational complexity. I mean, not only can I find the function, or is it easy to find it? I mean, in terms of computational complexity, how fast I can find a good approximation to my data. And that becomes, of course, an important issue when we talk about a lot of data and very complex functions. So the computational complexity becomes very, very important, the larger the problem. Now, one of the things that changed since the 80s, so that's, people have been doing this, and there are many clever ideas there, which I'm not going to, which are all essentially about these two things. I mean, how do you guarantee sample complexity, small sample complexity, and if possible, also the small computational complexity. Now, already then in the 80s, actually much earlier, people suggested different types of models which have a slightly different characteristic, which we now call neural networks. Actually, people call them neural networks already in the 40s and 50s, which are based on some sort of an attempt to mimic biology. And so essentially, if you think about neurons, they have this strange tendency to connect with each other, or to send dendrites and synapses to connect. And essentially, they do it not for any metabolic or biological, clearly biological reason, but for one simple things to gather information. And that's what they do. And so essentially, they collect information by connecting to other neurons. And already in the 40s, people conceptualized the neuron by this very simple, what we call linear threshold gate today, which essentially every neuron behaves roughly, very roughly, as an integrator of many inputs with some weights which are known as the synaptic efficacies, or the connectivities to other neurons. And we can, again, very roughly think about a neuron as a dot product with some weights w's of the other neurons that it's connecting to. So this, and then take some sort of a nonlinear function. So we sum w's times x's. The x's are the inputs, and it may be biased or shifted somehow, and so on. And then we put it through a nonlinearity, which is supposed to represent the firing of the neuron. It's either on or off. So the simplest nonlinearity is something like a sine or 0, 1. But this is not a very well-behaving function for all sorts of reasons. So usually we smooth the nonlinearity either by smoothing the sign like a sigmoid function, or smoothing so it can be something like a sigmoid, something like this, or it can be other even simpler things like rectifying linear function, what we call ReLUs. And this is actually what is used in many of those systems today. And the idea of neural network is just stack them together. And actually, when we talk about deep neural networks, we talk about many, many layers of these neurons, or these linear threshold gates, which are connected to each other. And let me eliminate the surprise yet. So essentially, this basic idea has been around since Rosenblatt in the 50s. And it came up and down and up and down many times since then, several times, at least three times. And since the late 2000s, around 2008, 9, 10, a group of persistent people who actually became very famous. I mean, Jeff Hinton, Jan LeCun, and Giorgio Bengio, and many others actually, who believed in this. They managed to bring this type of machines, I mean, this multi-layer feed-forward neural networks, which are essentially just linear threshold gate connected to each other, more or less, with all sorts of tricks like convolutions and other things which are playing there. But essentially, that's what it is, just many, many layers. So you take something like, let's say, the first layer can be just the pixels of an image, like, let's say, this picture of a dog, and the output should be the word dog, or just 1 if it's a dog and 0 if it's not dog. Or it could be a picture of me, or a picture of face, or a picture of much more complicated objects than dogs. But even dogs are hard to classify for using the classical standard of AI. And somehow the big surprise was that how do you train it? You take the error in the output, you average it over all the training data, and then you take the derivatives of the error, measured in various ways. I'm not going to get into it right now. And eventually, using the chain rule of derivatives, change by small changes by gradient descent of the error all the weights, with all sorts of variations on this theme, which you all know a lot about. I mean, so I can do stochastic gradient descent, or exact gradient descent, I can do all sorts of tricks, balancing and normalization and so on. But essentially, what I do is backpropagate those gradients of the error from the last layer all the way to the first layer. And I do it because it's a feed-forward just composition of functions. I can do it just using the chain rule of derivative approximately or exactly. It doesn't really matter. The big surprise is that this relatively simple, stupid machine and even stupider learning algorithm is doing amazingly well. Amazingly well, it means that on these problems of object recognition, it's essentially doing as well as human beings. And it solves classical problems which I didn't believe are going to be solved in my lifetime, like speech recognition, or like machine translation to some extent, and many, many other problems, control, playing Go, or whatever you want. Many, many other things.
So all these are based on gradient descent?
Yes. All these are based on various versions of gradient descent.
And that's why I need these.
It's a local small changes of the weights, yes. And eventually these things converge to a good solution. Now, this became one of the largest puzzles of our time in some sense, because since around 2006, so as I said, I mean, this became a big puzzle. And not only a big puzzle, I think I'm not exaggerating by saying this is one of the most fascinating, maybe hardest problems of our time, at least in computer science, or in this applied computer science. But not only, because those machines are extremely simple and we don't really understand why they work so well, what are the theoretical limits, what are theoretical guarantees we can give. One thing that of course, is immediately striking is that the number of parameters, tunable parameters in this type of models is much larger than the number of data points. So we are talking about models where we can have hundreds of millions of parameters. I mean, let's say the input is a megapixel image, which is not too big. We can actually have more than that. So we have essentially 1 million connections for every neuron in the next phase. So you immediately get into hundreds of millions tunable parameters in these models. And the number of examples is of order of hundreds of thousands, maybe. Order of magnitude smaller, or even 2 orders of magnitude smaller than the number of parameters. This is breaking. So essentially, this violates this iron rule of statistics that the number of tunable parameters should be of the same order as the number of points, of data points. But of course, it's not very surprising. In biology, we have it all the time. I mean, our brain has many more synapses than actually data that we train on. So we know that such models are possible. The question is, what actually happens in this type of models which makes them so well? So okay, so among many others, I'm trying to develop my own understanding. And it's a question, of course, that everybody who believes that he understands anything about machine learning is trying to have his own view and his own theory of why it works so well. And we are living in this great period that we can all say whatever we want for a while. And then at some point, I guess those theories will settle down to something. So I'm going to give you my own version of, which is information theoretic in nature of why it works. It's actually made out of 3 different twists that I make to the classical theories. First of all, what I call rethinking statistical learning theory, I move from what we call the worst case bounds, which is really supposed to dominate the worst case behavior of learning, which means, okay, given an example, I want to guarantee that the worst case error is small. That's what we try to do in theoretical computer science all the time. In this case, it has absolutely no chance. The worst case is uncontrollable, so we need to move to something like a typical behavior or average case. And this, of course, we can do and actually put some theoretical guarantees exactly when the problems get very large, because then we have some sort of concentration, statistical concentration of things which can, so we can bound the tails of the distribution by some sort of tricks. And this is essentially bringing us to the theories that deals with typical behavior. And of course, information theory is one of them. Information theory is very similar to statistical physics or statistical mechanics, which actually precedes it by 100 years, but essentially is the theory where typical behavior really dominates. And typical behavior is usually dominated by this notion of entropy and information, which essentially measure the number of typical configuration of a system, ignoring the tails. So that's something which I'm using very heavily, these ideas that are coming from statistical mechanics for me, but in the information theory view, they're actually simpler and cleaner than in statistical physics. And of course, what helps us here is that the problem grew. We are talking now about much larger problems than used to. So we actually introduced, I mean, I was among the people in the 80s who already did statistical physics of learning, but this had essentially 0 impact on the learning community because the problems were small and nobody was interested in the asymptotics of some very peculiar models. I mean, like 1 layer, who cares about it? But now we actually, in the era that everybody is doing very large-scale learning, and we actually need this typical behavior. The last and most important aspect of this theory is the connection between information theory, which is actually a static theory in the sense it has no sense of dynamics at all. It's a property of distributions when they're given or known, or at least implicitly known, and the dynamics of the training. I mean, the fact that we're actually using gradient descent with noise to train those models. So I'm going to tell you very briefly, give you my view. It's going to be very compressed. So please ask questions. So the view that I have is focusing on what I call information flow in the network. So what do I mean information flow in the network? So imagine that the input x, think about it as the pixels of the image, okay, of the image of a dog, let's say. So this can be a very high-dimensional variable, something like millions of images, and millions of pixels. So even if you think about each pixel just as 1 bit, it's already a very high-dimensional random variable. So I can't really characterize the distribution of it in any real sense in practice, but I know that this has what we call high entropy. I mean, it's a very high-dimensional random variable. Okay, and the label. Let's say that I'm talking now about the plain vanilla deep learning. So I'm just trying to classify. Given an image, let's say the label can be just 1 bit. Is it a dog or not? Or is it me or not me? Or something like this. Let's call the label y, okay? Just because I'm lack of imagination. So y is usually a very simple variable, can be just 1 bit. And of course, the problem is, and what I'm given is data, which is essentially a sample of this joint distribution of pictures which are labeled with a dog, and pictures which are labeled. So it's all supervised learning, and I'm given this sample of these statistics, okay? But now something. So this data is outside of my model. I mean, this is given in the world. And all I can do is sample this distribution, assuming that it's a stationary fixed distribution and something like this actually exists. But this is a reasonable assumption. And now the layers of the neural networks are essentially just maps of 1 layer to the next layer using these tunable connections. And once the connections I give, I can calculate the first layer from the input and the second layer from the first layer and so on. So these form what we call a Markov chain, given the weights. It's actually a Markov chain of deterministic functions, but even if there is noise there, I can think about it as a Markov chain in the classical sense. So there is a probability distribution that age I get some combination, some value given hi minus 1. Okay? And of course, the miracle of learning is that the last layer is such that the topology of the structure completely changed. I mean, so pictures which are essentially very similar, but one is dog and the other one is not dog, are now mapped to two different subsets very far apart, and I can separate them just with a hyperplane, essentially. Just cutting the data into two. Dogs are going to be on one side, non-dogs on the other side. So this looks like a miracle and a cascade of change of topologies, which I'm very much interested in. So now I'm going to talk a little bit more mathematically. So I'm interested in how much information each one of those layers captures about the input versus how well it predicts the label. And of course, the output y hat is the output of the network. Is not exactly y. It's supposed to be close to y eventually, but it's something else. I call it y hat. So there is a chain of transformation, of representation transformation, which I'm going to characterize using information theory.
I actually don't understand this picture very well. So you start off with this left-hand side, is that right?
Yes.
This is what you.
So that's the data. I'm given a sample of x's with y's. Okay. Y can be actually noisy. I mean, some people will call it a dog, some people will call it a cat. I don't know.
That left-hand picture is what you're trying to identify.
So I'm then trying to classify. Eventually, I'm going to try to predict if this picture is a picture of the dog by putting a new picture here.
I mean, I don't quite understand what this left. I don't understand the sequence of pictures. Could you say something more about that?
These pictures are just illustration that something strange happened in these layers, and some people. So we know that the first layer have some very general local features, like this is what happens in the visual system as well, some sort of a Gabor function or things like this. So that's what's plotting here. These are just pixels. I mean, it can be anything. And eventually, when you go higher and higher, we know that we get units here which are sensitive to much larger objects like faces or objects. So there is some sort of a hierarchy of details that get larger and larger when you have some coarsening of the image and something. I'm not sure that this is correct. I mean, it's certainly not essential in my story, but we actually see it also in the brain. Or we see cells that respond to some very specific places, very high in the cortex and so on. So this is what this is supposed to represent, but this is just to illustrate for those who know what it is. Okay.
Another way of saying is x is a vector, h1 is a vector, h2 is a vector.
Yeah. Each one of them is, I'm thinking about them as a high-dimensional random variable. Okay? So this x, h1, and so on are just random variables with very high dimension. Okay? So now I can actually talk or ask how much information flows in a sense that I have to define. So you can actually think about it as if the network, or at least I think about it as some sort of a cascade of nonlinear filters. I mean, they really throw away some information, goes through, and some information disappears. And I want to understand exactly how it happens. Okay? So just to make sure that we are on the same page, I need to introduce some functions, which I'm sure most of you heard about. So the first one is what we call the KL divergence, or the Kullbaum divergence, or the cross entropy, or the relative entropy. It has many, many different names, which is essentially just the average log likelihood ratio of two distributions. And this is a very fundamental function in information theory, in statistics, and many other places. This is a non-negative measure, which is 0 precisely when P and Q are almost always equal. And it has so many different meanings, I don't have time to give all of them now. What is important is that one particular function, which I call the mutual information, is exactly the scale divergence within the joint distribution of two variables and the product of their marginals, which means it's going to be 0 precisely when they're independent. Okay? And otherwise, it's a non-negative measure, which is precisely equal to the entropy of one of the variables minus the conditional entropy of the variable given the other one. So essentially, it's how much uncertainty was reduced about x when I know y. And it's a symmetric quantity, which with respect to x and y. And it obeys two things which I really need to use, I want to use. One of them is what we call the data processing inequality, which means that if I go along a Markov chain, information can only go down. So in particular, the information about the input and the label, the true label, the desired label, is going to go down when I go through the layers. An immediate consequence of this is this information is invariant to any invertible functions of both x and y. So, and this is actually a big problem, because it means that I can, for example, encrypt my data with some very complex function, and it will not change the information at all. So So information is not telling me anything about complexity, computational complexity. And that's really one of the reasons why people like Avi don't like information, because it's not a very useful thing in theory of complexity, as it is. Maybe I'm wrong.
I like it.
You like it? OK. Well, you have to be careful with it. So this is the reason. I mean, this is invariant to very complex computational transformation of my data. So information alone is not going to tell me the whole story. OK? So just something about measuring information. OK, so actually, I don't know, this may be a little bit too much now. But one of the, I'm going to show you a lot of simulation. We actually estimate information. And one of the attacks we got on our first papers on this is that we estimate information in a very crude way by using essentially binning of the variables. I'm going to talk, because we're talking about very high dimensions. So estimating information requires estimating the joint distribution in high dimension. This is in general impossible. I mean, it's exponential in the number of dimensions immediately. So what people do today, and actually we do also, is we use some sort of a variational approach, which turn out to be very, very, very useful to define information. This is based on really very elegant old mathematics of Donsker and Varadhan from the 80s. Which is essentially telling us that this scale divergence can be written as a supremum over all possible maps from my sample space to the reals of the expectation with respect to one probability distribution of the map of the function minus the log of the expectation with respect to the other one of the exponent of this function. This is actually very easy to prove and you have some intuition. Essentially, this achieves the maximum precisely when this function is the log likelihood ratio. So this is actually very nice, because even if I don't, and this you can easily verify, even if I don't know the function, I can now find a lower bound by searching a function in some class of functions. Let's say band-limited functions, or functions which polynomial of some finite degree, or whatever. And as long as this class is sufficiently rich, I'm going to get a better and better lower bound to the KL divergence. And so this turns the estimated information into an optimization problem, which surprisingly or not, I'm solving with another neural network. So essentially, we search for the function by training another neural network. This is an idea which is called sometimes a MINE, or mutual information neural estimation, which was suggested recently. But it's something which is nice, because it clearly tells you that mutual information, or even the KL divergence, I mean, of course, we use it to estimate information, but it's a general KL divergence, is actually depends on the ability to search in some function space. And if you are not limiting your function space in resolution and in terms of how many bins are there, how many different values they take, or some bounds on the derivative of the function, anything like this, it's going to be a very difficult problem. And of course, again, the problem I told you before, I encrypt my images with some very hard function, and this is going to look like noise. And actually, to estimate the information, I need my function to actually be able to decrypt it. And that's something which can be very difficult. OK, but that gives you a computational and optimization motivation of estimating information. And that's actually what we are using now in many of our games. OK, so
I have another general question. So when you're using gradient descent, you're not necessarily minimizing something, right?
You're minimizing the training error. That's what you're doing. Minimizing the fit to the data. Yeah. So you're actually minimizing something. When all those neural networks are very good in finding an approximation to a function that passes through data. That's what they do. So why don't finding this function which estimating mutual information? Okay. And that's precisely what a lot of people do today, not only me. It actually turns out to be a very interesting sport, how to estimate information reliably. So that's not an issue anymore, as far as I'm concerned. So now let's talk about information. I mean, so information, when it flows through the network, data processing inequality is telling me that the mutual information about the input with respect to every one of the layers is only going down. And the mutual information about the desired label, the true y, is also going down, because it's to the left of the whole chain. OK? And it's bounded by the entropy here and by the mutual information here. So I actually want to look at this mutual information. I'm going to skip some details. So this is a movie I'm showing in many, many talks, but it's always good to see it. So what you see here is what I call the information plan. So it's the information so T is the layer, or if you want the function that I'm looking for, any T, the information about the input X, and information about the label that this representation has. And what you see here is 100 independent random repetitions of the same neural network, where I initialize the weights, like everybody else, as a small Gaussian noise around 0, with a standard deviation of about 0.1 when the nonlinearity is over the 1, which means sigma or whatever it is. So this is a small noise. If you actually initialize it with 0, gradient descent is not going to take you anywhere because all the derivatives vanish. So you initialize it with small noise. Now, this turned out to be important, but what you see here in different colors are the layers of one particular neural network, which is not very important because you see exactly the same picture in essentially everything we look at. So just to explain it again, this is the information about the input. It is bounded by 12 bits in this case, so it's a very small network. And the information about that label is 1 bit is bounded by 1. And this blue here is the first hidden layer. The yellow is the second hidden layer. The pink is the third. And so on. Actually, there are 5 hidden layers here. So it's a six-layer neural network. And what is really surprising that you already see that it goes down very quickly. And the last hidden layer, which is really what I care about, in this case, at the beginning, has essentially 0 information about the label. So the prediction is essentially random. And very little information also about the input. It's 2, 3 bits, whatever. And of course, the scatter here is due to there's already something striking in this picture. And this is the fact that all these different random networks, completely independent from each other, just the architecture is the same, essentially concentrate in very specific region in this plane. We have to understand it. But now I'm going to show you what happens when you train the network with this gradient descent. What you see up there in the number that's running is the number of training epochs, between the number of cycles through the data that I'm doing in this training. So essentially, I'm doing something like 10,000 cycles. And if you follow these trajectories, it actually looks quite striking. I mean, so this is just a numerical experiment we did 3 years ago. So actually more than 3 years ago, but never mind, 4 years ago. Oops, I'm sorry. So I'm going to run it again. And I'm going to stop here, around 300 epochs. So what you see happens, of course, data processing inequality must be obeyed. So information only goes down. And there was some sort of a climb of all the layers. Of course, what I care about is the last hidden layer, because this is the one I want to really give me all the important information. So you see that after around 300 epochs, there's also this very nice concentration. Actually, we can prove that this concentration must happen under some very specific assumption about the nature of the data. But they actually really nicely concentrate. And you see that after 300 epochs, there's about, let's say, 0.6 bit, which is really not too good in terms of generalization. This actually measures generalization error because it's the true information about the label that the representation has. But for just a second, from 300 epochs all the way to 9,000 to 10,000, you see this very strange behavior. So all the layers come up, and eventually the last hidden layer moves to this very interesting point, which has essentially 1 bit about the label, which means perfect prediction of the label, and also more or less 1 bit about the data, which means it remembers only these 2 categories, 1 bit. So it managed to do what I want, what sometimes we call minimal sufficient statistic. I mean, I don't remember anything which I don't need to remember about the data. But what is really interesting is that all the layers are moving in this phase to the left. So essentially, if you actually look at the picture here, it looks something like this. This is just averaging these clouds. You see those traces. There are distinctly 2 phases. One of them is from A to C, where you move relatively quickly and improve the generalization. Actually, most of the layers even move a little bit to the right, which means they even gather information about the input. But from C to E, where most of the money lies, I mean, that's where you actually get good generalization, is a very slow process, and that happens with this additional, what I call compression, or moving to the left of all the points. So they forget, in some sense, information about the input. Yes? No. So this is a plain vanilla TensorFlow without any regularization. and without weight decay, or without, I don't know, dropout, or whatever people are using. And there are many, many ways of regularizing by force. So it's a fully connected, no convolutions at this point. Now, we see the same type of pictures. Of course, the details differ, but we see the same type of moving up and then moving to the left and high. Essentially, every net, including real problems like CIFAR and ImageNet and whatever, of course, it's much harder to estimate. But using this mutual information neural estimation, we can actually do it. And other people are doing it as well. So this is actually verified by many, many people. So the question I want to answer in the next 10 minutes is essentially what's going on here? Why is it so important? So first of all, as I said, I mean, when we first showed this, a lot of people argued whether it's actually general. So actually I read this. This is the general picture. So essentially, we understand now why the mutual information values concentrate. We understand the meaning of these two numbers. I'm just telling you very briefly. I about y is bounding generalization error, and I about x, which is really the strange thing. I mean, this compression, the fact that I'm actually forgetting information about the input, is directly related to the sample complexity. I mean, how many data points I need in order to achieve the generalization. And I can tell you very briefly, I can get into the proofs if you want, that every bit of compression of the representation at this point, the encoder of this representation is like every bit of compression simplifies the function class, which in a way which is equal to equivalent to doubling the data. So let me get into a little bit of a theory. So first of all, why do they concentrate? There was a question here? No.
Yeah.
Yes.
Can you just go back to the last slide?
Yes.
When we talk about concentration, the orange dots concentrated the previous slide.
No. So these are just simple points on this curve.
No, the previous slide. When you
Not only the orange, all of them concentrate. I mean, it's simply a very small problem, so you have this finite size effects. But if you look, essentially all the clouds follow very similar trajectories.
Yeah, but like, how come the orange dots concentrate, but the other layers don't? They like form much larger point clouds.
Yeah. Okay. So as I said, this is 12 bits of inputs, 1 bit of output. It's a what we call a very small problem. What I can prove is that once the input gets larger, I mean, let's say from 12 to 100 bits, and the concentration goes like 1 over square root of n essentially, like as you expect. N is the number of possible patterns here, so 2 to the 12, or 2 to the 100, whatever it is. And so you have a measured concentration in the same sense that you have it in statistical mechanics. I mean, so just like the air in this room is completely dominated by 2 numbers, energy and entropy, and a few other things. I don't care about other things. There are very few numbers that I need to know before I enter the room. There are very few numbers I need to know about this network. Actually, what I'm saying here is that only these 2 numbers, information about the input and information about the output, tell you essentially all the story in terms of the importance of the dynamics. That's already a very striking statement, because I'm telling you, out of those millions of parameters, you have to worry about these 2 numbers only. And now I just give you the gist of the idea of the proof. These log likelihood ratios which appear in the mutual information essentially factorize if there is some sort of locality. So if let's say an image, the probability of a pixel to get a certain color is almost completely determined by the environment of this image. So if I give you, let's say, 10 or 100 patch of 100 pixels around this image, I know almost certainly what this pixel is going to be. It's an assumption. So under the assumption of locality, which is actually hidden in many, many different ways, we actually heard about this type of assumption just recently with the Laplacians. They can hide it in very fancy ways, but that's essentially the assumption that there is some local factorization of the distributions. And under this assumption, the product goes into sums which average. Okay, so that's very, very general. And so if there is this local factorization, almost local factorization, it happens in image recognition, it happens in speech, it happens in language, it happens that essentially the local correlations or the local dependencies dominate the picture. Okay, so that's easy to understand and actually even verify theoretically, quantitatively, in what sense I have concentration of these quantities. So this is what physicists usually call good order parameters. On the other way, you see that these two numbers really seem to follow a very interesting trajectory in this plan, per layer, layer by layer, in a way which I really need to understand. So the first question is really, OK, so this is a slightly different view of the same story. This is the number of epochs here. The dynamics is in color. So black is 0, yellow is 10,000. And it's linear. And what you see here is what happens if I reduce the data. So instead of training on 80% of the patterns, remember, this is a small problem. There are only 4,096 inputs, possible inputs. 80% is something like 3,000. And this is only 5% of the data, something like 200. So of course, the first thing we wanted to see is what is the effect of small data size. And what you see in this trajectory is quite striking. Actually, the first phase, I mean, coming up to this green line, is essentially the same. Even very small data brings you to this plateau of error. But then if I don't have enough data, I'm losing information in this compression phase. I'm actually forgetting important, relevant information. And therefore, I do what you may call overfitting, overcompression. And of course, somewhere in between is somewhere in between. What I actually argue, again, I don't have much time to convince you, that we actually have a theory for these lines. I mean, what are these lines in the plan? And that's really the striking new feature of this story. So essentially, if you really look at this neural network, you can think about each layer as having an encoder. Sorry about so T here is the layer, having an encoder, which is the map from the input to the layer, and having a decoder, which is the map from the layer to the label. Actually, I can think about the optimal decoder. Given this representation, what is the best possible decoder of the information about y from this representation? So the encoder is really the main story. So and that's what we actually plot there. I plot the information, the mutual information of the encoder versus the mutual information of the optimal decoder. And I actually argue that the mutual information of the encoder is completely controlling the sample complexity of the problem, which means how much the typical sample complexity, remember, it's not a worst case bound, but it has the nature of the bounds that you know from let's say, PAC or whatever, if you know some learning theory. Essentially, what I'm saying is that the gap, how well I predict out of my training is completely dominated by the information that this representation has about the label. And the effective dimensionality of the class of functions that I'm using, that I'm actually emerge at this particular representation. So let's say I map my data to some intermediate layer, and that's my data now. And I'm asking how many examples I need from this representation in order to predict my label. And that goes like 2 to the compressed representation. So of course, this becomes interesting only when the data size is of order of, or the information is of order of log the size of the data. Otherwise, it's not a very interesting bound. But this is really striking. The information goes to the exponent here, which means that every bit of compression is essentially equivalent to doubling the data. And the confidence log of 1 over delta is completely negligible in these large problems. Forget it. So that's the type. It's really crude in the way I wrote it here, because there are some corrections, logarithmic corrections here. But that's essentially the behavior. So that's a really striking. Every bit that the layers move to the left is effectively reducing the function class. Yes?
Where did you use the particular properties of the
information?
of the network for which you have these results? I mean, do you use the fact that each layer computes a linear function? And
No, I'm not using. The only thing I'm using.
So it can be a network of anything as long as it's a markov chain.
Yes. Essentially, what I'm saying is that a cascade representation. That's why I actually argue that the same theory should apply to the brain or to other things which have this more or less layered structure or cascade of representations.
And what do you use? It doesn't matter for the training process of gradient.
OK, this I'm going to talk. The training process governs this interesting dynamics. And that, of course, depends on the way you train your network and whether it's stochastic or not and so on. Now, so the gist of the theory, by the way, just for those of you who know some information theory, how information comes into this game. So how many of you at least vaguely remember the proofs of Shannon's coding theorem? I can't really. So there's the same argument exactly there. There's a counting argument, which tells me If I want, essentially what I want is to see how many possible patterns are here, and that's exponential in the entropy, in the large typical behavior, and how many cells of internal representation I have, which essentially are distinguishable in terms of maps. Whatever the map is, you can think about the layers as just partitioning my input space. So this is dominated by the conditional entropy, and then the possible number of functions is 2 to the number of cells here, number of different, and this is 2 to the hx divided by 2 to the hx given t. It's precisely 2 to the I. So I get I as the dominating factor, the one that actually allows me to count the number of possible configurations in a central layer. This is the information. That's how ITX comes into the game. So so the cardinality bound that you're used to seeing in learning theory goes from 2 to the cardinality of x to 2 to the cardinality of the layer. And this goes like 2 to the I. So this essentially gives me this double exponents really gives me this type of bound. So this is really surprising. At least to me it was very surprising. But now we understand pretty well how it works. Now, the interesting story, and I really don't have time to go into the details of the dual formulation, but I want to give you why does it happen? How is gradient descent really doing it? So what you see here is the same picture of the information plane trajectories. But here you see the error, the training error. It's actually a generalization error, but it's the same thing here, almost the same thing. And what is really striking is that this motion to the left, or what I call the compression of the representation, starts exactly when the error saturates. So there's a very nice knee that we always see in this training, the very fast descent in the error first, and then a very slow, which takes forever, a decrease of the error. It's not zero, the error is still not, otherwise the gradients will vanish, but at least the fluctuated, if you use stochastic gradient descent, the error now starts to be very noisy. The gradients become very noisy, and that's precisely the thing that is pushing the layers layer by layer to the left. OK, so this gives us a very strong hint that there's something in the nature of the gradients of the optimization which is really changing here and responsible for this change in behavior of the information plane. So let's try to look at the gradients. So that's, again, something which we did, and nobody believed us, and since then many, many people did. So what we see here, this is my toy network. OK, it has this very peculiar, very specific Eiffel Tower structure, so the layers get narrower and narrower. But as I said, I mean, this is something we see in many architectures across many, many different applications. So what you see here is the mean magnitude of the gradient per weight in every one of the layers. So the layers have different colors, and we normalize it so they all have more or less the same value at the beginning. And this is the standard deviation over the mini batches. So I'm talking about noisy gradients. We're doing stochastic gradient descent. Actually, even when you go to very large batches, so essentially you use the clean gradient, you still see this type of phenomena, at least some remains of it. And that's something which I guess I argue with some people here in particular, like Sanjeev and maybe others who argue that the stochastic noise is not so important. But in this case, you see very, very clear change in the nature of the gradient. So this is a log-log plot. Yeah? So up to about 300 epochs, which is here, the SNR, I mean the signal, the gradient, the mean to the standard deviation, is very high. It's about a factor of 100, which means for engineers 20 dB signal. I mean, it's a very clean gradient. Once I go beyond 300 epochs, there is a flip in this picture. The gradients slightly go down, so it's a log-log plot. You don't see a big change, so an order of magnitude. There's actually a very nice dispersion. The gradient is larger at the lower at the first layers, and then the noise accumulates. So that's what you see here. But the standard deviation jumps, and essentially beyond this point, the fluctuations in the gradients are much higher than the mean, or in what I call low SNR, low signal-to-noise ratio. Sorry?
This plot, is it
everything is trained with cross entropy, just because this is actually exactly the mutual information. So it's easier for me, but it doesn't really matter. You see the same phenomena if you train it with L2 or with essentially every loss that I see. But there are differences. But cross entropy is really giving you this type of flip in the gradient. And what is really interesting, OK, so this SNR, this is essentially clean gradients. It moves very quickly, what we call in physics drift. I mean, essentially, you move linearly. The waves grow linearly with time. And once you move to this, you are dominated by the statistical fluctuations of the gradient. So from here, it's what we physicists like to call diffusion. Random walks. Now, the interesting question now is how does this random walk really affecting the phenomena that I described? I mean, how is it compressing the representation? And why is it that I generalize better, actually? So just to convince you that this is really what happens, this is the average norm of the weights. Remember, I'm not using any regularization. So the weights keep growing. And in this phase, they grow linearly. So this is, again, a log-log plot, more or less linearly with time in the first phase, and sublinearly with an exponent which is more or less half, or even less than half. That's exactly what you expect from a random walk. When a random walk, the weights will grow like square root of t, a true random walk. OK, so and there's really a very clear distinction. You see this change of slope, and you see it actually. I'll show you much more convincing pictures like this. So, and again, we see it again and again in many, many different networks and in many different problems. This MNIST, this is, and we see this type of compression moving up and then moving down. And there's also something very peculiar, which I begin to understand, which is where exactly these layers stop. I mean, they don't get all the way to the end. They stop in different representations, which is really telling us something about the nature of the encoder. I mean, what is actually encoded in this layer? Now, so there are two. I'm really running out of time. There are two results that I really want to convey to you. The first one, which I consider very important, is that we actually know where these layers converge to. So there's something called, OK, so the question, let me start with this. The question of, this information plan is not, I didn't just got it out of my head suddenly. This is precisely, there is a theoretical bound, which is related to the rate distortion bound in communication. Some of you may know. So essentially, I can calculate, given the joint distribution of x and y, I can solve this variational problem, minimize the information of the encoder, subject to a constraint of the information of the decoder. So I'm giving you, there's a line here. This is the information of the encoder I want to guarantee. What is this place? What is the minimum information of the encoder given some constraint on the decoder? This is what I called, I don't know if it was not a very good choice of name, but it was stuck. This is what I call the information bottleneck problem. Already 20 years ago. Actually done, this particular observation was done here in Princeton with Bill Bialik and others. So in 1999. So essentially, the fact that we can actually solve this problem and say what is the theoretical limit given a joint distribution of x and y, and this particular variational problem has a very specific solution. This is the explicit encoder. It's essentially exponential in the KL divergence between the prediction of y from the true data and the information of y from the representation, as you can imagine. So if I don't have any error, it will be perfect prediction. But actually, if there is some stochasticity, it's enough that this probability of y given x is not exactly 1 or 0, that there is already a continuous smooth line, which is the boundary. So there are no representations, no matter where they came from, above this line. And the only representation below this line, actually, there's also a lower limit, which is called sometimes the privacy Fallon, which is also an interesting question, but I'm not going to talk about it. So iterating these equations is essentially giving me this line. Theoretical information, theoretic bound of information that I can get about the label given information about the interpretation. And now my conjecture was, and we published it in 2016 with Noga Zaslavsky, is that nothing should prevent the layers of a neural network to achieve this bound eventually. So the prediction somehow gradient descent is taking me to the bound. Until we started to look at the simulations, which were done by Ravid Zim, and then we were actually struck that it's not only achieving this bound, but there is really this phase of pushing it to the left as much as possible. So my argument is that for most neural networks, and under many assumptions I have to make about the nature of the data, like this local factorization and so on, the layers are going to lie on the information bottleneck bound, if there's enough data. What is really nice about it is that this gives me an explicit expression which is architecture model independent, depends only on the rule of the optimal encoder and the optimal decoder at any given. Beta here is a Lagrange multiplier which determines where you are on this curve. So essentially beta is 1 over the slope of the curve. So given beta, okay, and once I look at these layers, I just have to put the information bottleneck line if I can calculate it. Of course, I can't calculate it in general because I don't have the joint distribution of x and y. But for some problems, artificial problems like the one I showed you, I can do it. And indeed, when we actually look at the network I showed you, this is what happens. This is the theoretical bound, the blue line. And these are the scatter of the layers. And you see that within the statistical error of this small problem, this is an asymptotic bound. Yeah? So they converge very clearly to the layer. So, and every one of the layers has a specific beta, specific value of this Lagrange multiplier. So that's already very satisfying because now I have an explanation. I can really tell you each of these layers is representing this particular, and you see this is stretched, but it's only the last 2% of the curve. It's very, very high. Okay, so we begin to have something like a theory that tells us what each layer represents. But the question is, first of all, okay, what happens if we have finite data? And that indeed is a question that finite data is here. This is a question we have been asking long ago with Ohad Shamir and Sivan Sabato already in 2008. What if I actually have a finite sample? Now, if you remember my estimate of information, it depends on the expectations with respect to P and Q. If you have an empirical expectation, these are going to diverge, and you have only a bound which bound the difference between the expectation and empirical, the same empirical convergence results that we're all using all the time. And if you actually apply this bound, you see that the less you compress, the worse is your estimate. So essentially, the true information is bounded by the empirical information plus square root of 2 to the I over m, essentially. Which again tell you that you should compress in order to generalize. Because you're actually going to be on the red line and not on the black line if you are using finite data. So the best you can do, this is of course very exaggerated. There are always two losses that you must suffer. One of them is what I call the compression loss, which is the fact that the black line is going down. And the second one is the difference between the black and the red, which is the finite sample loss, which is this gap. So this is just the same bound I showed you before. In this guy, the same is exactly 2 to the I over m is the dominating factor here. Now, okay, so you see that from this type of analysis that the layers effectively must go to the left in order to generalize, if you have finite data. Okay, so now the interesting question is why is SGD or stochastic gradient descent actually doing this this compression? So again, I'm only going to give you some intuition and stop me when I am out of time because I have no idea how much time I have. So essentially here I'm talking about optimization. I know that there are many experts to optimization here. So I know that I'm working in a minefield, but let me say it anyway. So essentially what this story is telling us, the beginning of this gradient flow is slow, but then you move fast, and then you actually fall into some sort of a low-dimensional manifold, some sort of a canyon, which is the canyon of all good solutions. It's actually there are infinitely many of them. Now, so this is the first phase. I'm actually moving on a cliff or somewhere and then I fall down into something. And this is this, and then this canyon is dominated locally by a covariance matrix or Hessian matrix of the error, which has a very skewed structure. There are very few dimensions which are protected in the sense that changes of the weights in these directions is going to hurt my error. So these are relevant dimensions. And there are many others, actually most of the millions dimensions that are there, which are irrelevant, which means I can change the weights in these directions without hurting the error. So that's the basic linear picture. Now I start introducing noise. So it's going to diffuse. But where is it going to diffuse? It's going to diffuse mostly in the irrelevant dimensions, because it's actually like diffusing in a canyon. I mean, so you're moving mostly in the direction which don't affect your error. Now this diffusion, so I actually separate the weights between two layers into those that are dominated by the projection, the optimal projection that keeps all the information about the label, and then something which accumulates during this noisy phase. So this essentially is an integration of a random walk, so this is some sort of a Wiener process. And the next layer, tk plus 1, is a nonlinear function of this matrix wk times the previous layer, plus something which is delta wk times the layer, which behaves like noise. So this is an assumption, and that this random matrix is a really random matrix. And when you actually multiply it by the previous layer, you get something which is effectively a Gaussian noise. In high dimension, this is provable. It's actually very closely related to this neural tangent kernel that people are using here and other places. This is the same line of ideas, but in a different way. But then I can think about the information, the mutual information between two consecutive layers as bounded by the mutual information of this linear function, Wt plus noise. This is what we call in information theory a Gaussian channel. And the capacity, the maximum information possible there in a Gaussian channel is log or half log of the 1 plus the signal to noise ratio. So the signal is W times T, and the noise is delta W times T, the T goes away, and you get this is the signal to noise ratio in each one of the dimensions. So now you just diagonalize it, and you get this type of result, that the mutual information between two consecutive layers is bounded by a constant which depends on the layer, plus something which decays with the number of iterations, like a power law, which is the way the signal to noise ratio decays. And that's a very nice prediction, because actually telling me that the information, the time to converge is going to decrease with the number of layers as a power law. Actually, so there's an immediate, well, again, I don't have time to go into all the details, but essentially you diagonalize it in this matrix, the CCA matrix, and then separate the relevant from the irrelevant directions, and say that in all the irrelevant dimension, you're doing diffusion with an exponent alpha, which is half, let's say, in classical diffusion. And this gives us this particular prediction. The time to converge to a good solution as a function of the number of the layers should scale with the number of the layer with a negative power minus 1 over alpha. OK, so let's check this. This is easy to check numerically. You don't need to estimate information. All you need to do is to calculate the number of iterations to converge versus the layers in the network. And what we see is this is for our small problem first. You see very nice power laws. It's a log-log plot. And the exponent seems to be very close to half. OK? So remember, this is a little bit counterintuitive. More layers converge faster. But faster in terms of number of iterations, not necessarily computation time, because the more layers you have, a lot more computation, of course. But this is, of course, the question is, OK, so why of course, it shouldn't go forever. And indeed, if you increase the number of layers beyond a certain points, so you get this power law up to some number of layers, and then it bounces back. OK, this you can see it here. So the time actually goes up again. So there's some sort of an optimal number of layers for which I convert the fastest. OK, for any problem. Now, we did it for MNIST, by the way. We see exactly the same thing. The exponent is slightly different. We try to do it for much larger problems. It's harder, but it's actually not hard. Anyone can do this. You don't need to estimate information. You just count number of iterations versus number of layers. That's it. The only problem is to extend the architecture in some regular manner by adding layers of the same width or something like this. So this is something I challenge any one of you to do. And you really see this very nice minimum. And the beginning is a log-log, is a very nice power law. OK, so now the really interesting question comes. What can I say about the location of each layer? And why a certain number of layers seem to be good, and when I extend it. So if you think about this prediction that the time goes like a power law, it's actually depends on the assumption that each one of the layers is able to filter out different information about the input. So think about it as filters. Each one of them is separating different frequencies. then it's going to be most efficient. But if there is overlap, if the layer is actually doing exactly the same thing, you're not going to gain anything. So this is, again, an information theoretic idea which implies directly to the dynamics of the training. And indeed, we see it in many different ways. I know I have to stop. I just want to tell you the most fascinating aspect of this theory, which is really something like a beginning of a theory, in the sense that it's actually giving me predictions of what happens in every layer of a deep neural network, why it's close to optimal, because actually reaching this information theoretic bound, why you can't do better even if you come from outer space, I don't care where you are, and also now the beginning of what each layer is doing. So again, remember, if you look at those curves, we actually see those interesting points. So this is actually, again, this is the same manifestation. If you add more layers, you converge faster. You see it here in this picture. But you also see that eventually when you add more layers, they stay in very specific points. And I can show you that even if you scramble the examples, change the order, change the initial conditions, change many things, you still get to the same points, more or less in each layer. So what's so special about this point? And you see that you're stuck there. I mean, the reason I showed it is you see that at the endpoint, which is yellow, half of the iterations actually got very close to it. So which means sort of slowing down. OK, so this brings me to a much more interesting dynamical system question, which is what slows down gradient descent? OK, you all know if the derivatives vanish in some directions, I get this what we call critical slowing down. And so I can actually calculate. The question is, are there critical points in this story? And of course, there are. So this, again, I'm now switching language. I'm not sure I catch all of you. I'm talking in the story of dynamical system now. So essentially, there are points on these curves, information versus beta. If you actually look at this information curve, instead of information about input and versus information about output, you look at both of them as a function of this slope. It is beta. And what you see is that there are very clear points where you have discontinuous derivative, or what we call cusps. And this discontinuous derivative means that there is some sort of phase transition, a second-order phase transition in this point, which means that the topology, there's some sort of merge of partitions or change of the topology of the representation. And we actually analyzed, with a series of works with Noga and a few other students, analyzed those critical points. So essentially what we know happens there, so essentially we just take we know that we are already on the information line, information theoretic line, so we have actually an explicit expression for the encoder and the decoder, and we just do a stability analysis, never mind how I do it. Eventually we got a linear, an eigenvalue problem, which really tells you the whole story. Okay, this is a little bit too much for now. Yeah, maybe this. So there's a matrix which I can calculate just from the encoder and the decoder, which I know analytically for some problems. And when this matrix becomes singular, which means I need another solution for this derivative, I have a concrete prediction of those critical betas. And we actually have an algorithm which takes us from one critical to another critical. What is really interesting, and that near these critical points, there is what we call critical slowing down. So the convergence time of the algorithm, the number of iterations, explodes and diverge precisely at those critical points where the representation change. OK, so this is the beginning of another talk, if you want, on what is the connection between those criticalities and the location of the layers. But what I can tell you is that for these simple problems, where we can actually predict exactly where are those changes of topology, the layers are going to get stuck precisely at these critical slowing down points. So that's, again, a very nice connection between the theory of dynamical systems and the theory of representation in learning, which I don't think many others are doing in this way.
I think we're running out of time.
Yeah, we're running out of time, and I finished my talk. OK. So let me just summarize briefly. The first message is that only 2 numbers per layer are really important to talk about large systems, the information about the layer. Most of the advantage that we see in many layers is computational, in the sense that you actually converge faster with more layers, up to a point, and that there are those critical points which are telling us where the layers are going to converge to, and it's happening because there's a critical slowing down. I mean, you don't really pass this point so easily. And essentially, the fact that the layers actually come from below and eventually slide on this information curve is really giving us a very strong prediction what happens. And actually, there are some solvable, exactly solvable neural network models which you can now, where has some symmetries and so on. But I think I'll just stop here and thank you. All right, thank you very much.